So, what is the calculated lattice enthalpy of formation of aluminium iodide given the following data? So let's just have a look at the data that we have here. So we're given ionization energies of aluminium. They're all endothermic processes because we are pulling electrons out, of course, and as we pull each subsequent electron out, we have less electron-electron repulsion, and therefore overall it's more difficult to pull the next electron out. Fourth ionization energy of aluminium will be very large because the electron will be in a lower energy level and therefore will be much more difficult to pull out. Enthalpy of atomization of aluminium, there of course we are breaking the metallic bonding with aluminium, going from a solid aluminium to gaseous aluminium atoms. In terms of iodine, we're given the bond enthalpy and the enthalpy of sublimation. Of course, bond enthalpy breaking iodine bond in the gaseous molecules, and enthalpy of sublimation conversion of the solid iodine to iodine vapor. Iodine electron affinity, dropping an electron into your gaseous atoms of iodine, -295 for this. Interactions between the electron and the positive nucleus of the atom, of course, is going to be an exothermic process. Also exothermic process in this particular case is the enthalpy of formation of aluminium iodide. So let's start and have a look and just see if we can work out what we need to do for this.
Hi all. Just a point about the next section. I'll start talking about the enthalpy of formation of aluminium iodide when I should be talking about the lattice enthalpy of formation of aluminium iodide. In other words, going from the gaseous ions to the solid lattice structure. Sorry about that.
Well, essentially what we've got to do is we've got to create a Born Haber cycle for this reaction, and we can start with our enthalpy of formation. We're going to form aluminium iodide. Here's our aluminium iodide, AlI3 solid, and of course we're trying to find the enthalpy of formation of aluminium iodide. That is forming our compound, our solid aluminium iodide, from its gaseous ions. So let's have our gaseous ions here. Al gaseous 3+, and iodine 3I- gaseous. Now that's our lattice enthalpy of formation that we're trying to determine. That it tends to be a value that cannot be determined experimentally. One that can be determined experimentally is the enthalpy of formation, the standard enthalpy of formation of aluminium fluoride. In other words, elements in their standard states there will give us our enthalpy, our standard enthalpy of formation of aluminium iodide. Of course, we're going to need not just 2 iodine atoms but 3, so it's got to be 3/2 I2. Now the rest of the process is essentially working out how to get from our elements in their standard states to the gaseous ions. And if you think about it, what we have to do is going to be based around, again, the definitions. Work backwards. Here we've got gaseous aluminium ions. Well, we get our gaseous aluminium ions by pulling out the electrons from a gaseous atom. So we're going to need to convert our aluminium solid into a gas. Our iodide ions, of course, we get those from dropping electrons into gaseous iodine atoms. So we've got to convert our iodine solid to gaseous iodine atoms in some way. So that is the process that's going to be involved. So let's go through the steps, shall we? Starting off with aluminium, shall we? So let's go up to aluminium gas. So we're on the right track for aluminium, like that. That, of course, is our enthalpy of atomization of aluminium. We then need to atomize our iodine. Sorry, going to 3 iodine atoms, like that. But we do have a slight problem here, and the problem that we have is that if we look at the data that we haven't got enthalpy of atomization. But what we have got is enthalpy of sublimation and bond enthalpies. And we can really make those two essentially do the same sort of thing, because iodine bond enthalpy will make our gaseous iodine atoms from our gaseous iodine molecules. And where do we get our iodine molecules gaseous from? Well, enthalpy of sublimation. I2 solid going to I2 gas, like that. So that's where we get our values from. So therefore, let's get rid of that process, like that, and move on to the processes that we do have enthalpy of sublimation for our iodine. So we can go to Al gaseous plus 3/2 iodine gaseous, like that. And then think about our bond enthalpy. Oh, before we do, of course, enthalpy of sublimation is for 1 mole of iodine. We've only got 3/2. So therefore, that's going to be 3/2 the enthalpy of sublimation. And in a similar sort of way, to get from gaseous aluminium molecules, sorry, gaseous iodine molecules to gaseous iodine atoms. Gaseous, there we go. Okay, we're going to also need our bond enthalpy, our iodine bond enthalpy, but only 3/2 of those. So we're well on our way. All that we really need to do now is to get the electrons out of aluminium and drop our electrons in, so we can have the first ionization energy of aluminium, second ionization energy of aluminium, and the third ionization energy of aluminium. So we're going to go to Al plus gaseous, Al2 plus gaseous, Al3 plus gaseous. Removing 1 electron first, then removal of a total of 2 electrons, and then a removal of a total of 3 electrons. Notice that totals of electrons there. In each of those cases, we're not pulling 2 electrons out for the second ionization energy. We're just adding the electrons up that we have. And then we've just got to drop those electrons into the iodine atoms, and that, of course, is electron affinity. So let's just fill the rest. So this is our first ionization energy, second ionization energy, third ionization energy, and then we have, of course, the electron affinity, delta H, let's call it EA. Okay, and we've got 3 of those. So there we have built up our Born Haber cycle. In the next episode I'll show you how to do the calculations.